I'm Tomaso Poggio, and this is a class that has been going on at MIT for probably 28 years. It's, I think, the oldest machine learning class at MIT. We hope also it's the most advanced one because it changes every year. There are the other instructors that we've seen quite a lot during the course are Lorenzo, Rosasco, step up, Sasha Raklin, and the most important people for you are the TAs. And Jay is not here right now. David, is David around?
He's late.
Sorry?
He's late.
Okay. Natalie, is he around?
He's over there.
Okay, over there. And Michael Lee is over there. Okay. I think we are streaming if anybody is interested in sitting down, and the coordinate for streaming should be on that whiteboard, right?
Yeah, so go on YouTube, look for CBMM, and then over there you should see a live stream.
Right. So if you want to sit down, you can go
You can just watch
outside.
on your laptop. On our board.
Okay, today, of course, is a very light introduction, a motivation of the class. That's the plan. Some words about logistics, what we plan to accomplish, what is our rules for grading your work and the kind of things we're going to do. And then I'll go into a motivation of this course in a broader context of what's going on in science, in AI at MIT, including the recent quest for intelligence was announced a few months ago. I'll tell you a little bit about statistical learning theory, just as a way to mention some terms and some concepts that we'll find in the class, so to get you a feeling of the kind of things you'll be hearing. And then some fun with old and new applications of machine learning, mainly to show how broad it is, and there was a lot going on even before deep learning. And then a few words about deep learning from the theory point of view, the things that we'll discuss during the course. What we have in the course is essentially 3 topics on which we focus. One is algorithms and theory. The second one is mainly regularization techniques and kernel machines and online supervised learning. And the third topic is deep learning and the beginning of a theory about it. And the goal is to provide you with, the theoretical knowledge that you should have in order to have a good intuition of how to approach new problems and solve new applications. Okay. In the process, I'll tell you that machine learning is a great area of science. Is natural science, is engineering, is money, because you can get rich out of it. It's philosophy, because it gives you some foundations for explaining what it means to do science itself. And the goal of learning is, of course, the goal of ultimately understanding human intelligence and replicating intelligence in machines once you understand it. So, it's a big motivation for you to attend the class, a set of big motivations. Now, let's go into the logistic of this. So, Lorenzo, do you want to?
Well, yeah, so the next few slides are just mostly rule of the game.
So most classes are going to be here Monday, Wednesday, same time as today. There are a couple of exceptions. You can see them at the bottom. I don't know where that room is, but you can find it on MIT map, and the dates are over there. There's going to be office hours. The time slot we fixed is Friday, 1 to 2 p.m. The lounge is a couple of floors upstairs on this side on the main street side of this building. So you probably get lost a couple of times and then you find it. The website should be basically online. Is the usual one. Playing tricks on me. Playing tricks on me.
This one.
I don't know what I have to say. So if you change it, I'm lost. It's here. All right. So there is a website. It's over there. Is the usual URL. There is all the links to the previous years, so you can see the difference in the content. There's going to be a mailing list that we're setting up. There is a mailing list to contact us, and there's a mailing list that we're going to use to contact you for various kind of communication. So we're going to probably next class tell you how to subscribe to that. We're going to use Stellar, so the TAs are going to get in touch about that, mostly for handling the PSET assignments. And, well, I think that's basically it for basic informations. Stop me if you have a further question. Just wait a couple of seconds that I finish to bore you with all. We're going to give you out a bunch of materials. Several of the classes overlap with previous years, so you're going to find videos on YouTube. We're going to try, Sasha and I, at least to give out, and probably Tommy too, to give out slides of the classes, but most of the lectures are actually going to be on the board. And for some part of it, there are some notes available that cover much more. They're more like reference material for studying. So we're going to give you all this material. This is just at a glance the syllabus. It's considerably different from last year's syllabus. Basically, it overlaps with last year mostly for the first roughly 10 lectures about algorithms. So last year, most of the course was just reviewing advanced algorithms. Here we focus mostly on basic algorithms, so basic regularization algorithm in the first couple of weeks, then a bunch of slightly more advanced ideas like using stochastic gradients, what is now called implicit regularization or early stopping, sketching, the idea of sparsity, and so on. We're going to move on to discuss neural networks, and this is going to be emphasis is going to be on computational algorithmic principles. Then we're going to switch gears, and we are also switch instructor to some extent. And so I'm going to be taking care of this first part. Then there's going to be Sasha. I don't know if you want to say a few words about this stuff. So I'll keep on going. Essentially, the first few lectures are, again, like kind of foundational, classical concept in statistical learning theory, like generalization, consistency, uniform convergence, Rademacher complexity. Then more advanced kind of bounds are presented based on margin, stability, privacy, information theory. And then there start to be somewhat a series of lectures dealing with theory of deep learning, mixing up both statistical aspects, so again bound, but also approximation theory, optimization aspects, things like minima, landscape of minima, and so on and so forth. And the final dessert, I think, is usually something about mixing up machine learning back to the brain, and Tom is going to tell you a bit about that. So again, the material online give you reference to all the stuff that was done in the past, and so you can compare a bit what's new. Going to the important part, grading policies. Essentially, again, this is a bit different from past years. So we decided this year we're going to try to follow this plan. This should be official. So 6 problem set, roughly 1 every 2 weeks. They account for 60% of your final grade. Each one of them is going to be 2-3 questions. The typical PSET is either exercises where you're required to do some calculations or some MATLAB assignment, usually. You will have 1 week to do this and return the PSETs. I'm going to tell you about late policy in a second. We're going to require you to typeset everything in LaTeX and submit it to Stellar. And then I think Michael tell me also to give a printout the following week, or not really? Okay, so I was not sure about that. So probably not. So it's only going to be on Stellar. Okay, and that's one of the main reasons we're going to do this. So we can get rid of this. So forget about this printed submission next class. Not going to happen. The other 30% of your final grade is gonna be based on your final project, and I'm gonna tell you a few more words. We're gonna tell you a few more words in a second. And finally, we are kind of keen on participation, despite the fact that we prevent you from actually sitting down properly in the class. So we'd like to have an idea of how many people are coming to class and how much you're attending. We put quite a bit of effort, try to make somewhat sophisticated material accessible. And so we try to, as Tommy said, this is an advanced course. We assume and we give for granted that you actually took machine learning classes, not because we go super fancy and complicated, but because from a conceptual point of view, you assume you've already thought about what is overfitting. What does it mean that you build models that you have to do with both statistics and computation? So if you have never seen this, you're gonna hit the wall pretty fast, pretty soon, okay? And so coming to class is our way to try to help you with that no matter what. Problem set, sorry. Problem set is basically what I told you a minute ago. The main thing are the dates. You can read them there. These are tentative-ish/official. We're going to try to stick to it. It should be possible. There should be a good timing. We start in a couple of weeks and we keep on going until December. Late policy, essentially you have a budget of 4 days that you can spend throughout the semester, okay? So you can accumulate up to 4 days without paying any price for your delays. You can spend whole 4 days for the first PSET, then you are not in a good shape for the other PSETs. Max 2 per, sorry, so you cannot do that. So it's max 2 per PSET. So you're going to be in a decent shape the next ones. Once you spend your budget, then we start to take crazily amount of points away. So 50% per additional day, okay? All this stuff we're going to put on the website if it's not already there. Projects type. It's pretty broad, as you see. Very quick. It's like theory, algorithm, application, coding, Wikipedia. Let me just tell you two things. What I mean by this. Here, the emphasis is basically on what you're going to spend time. You're doing some math, reading about algorithm, coding up something, or applying something. There are two things you might want to know. One, if you plan to use your own data and to try to develop solutions for specific applications, we're not going to. You're going to probably spend a substantial amount of time preparing your data set and, acquiring your data set, massaging your data set. We don't care. That's your job. Okay, it's your choice. You're inflicting that to yourself. We're only going to evaluate you for whatever you do on the machine learning side. Okay, so we don't discourage that. We know that a lot of you want to use machine learning for your own application, but you have to show us what you've done on top of whatever, your application is. Okay, so that's somewhat. It's not just I'm going to apply a deep learning neural network to this kind of data. Okay, you have to do a bit more. You have to tell us exactly what you do there. The last bit is the Wikipedia. What we mean by that, essentially in the past, it was quite useful and successful to replace the typical survey-like work. I like this topic, I want to do a survey. We try to do the same thing with the idea of putting it and eventually do put it in Wikipedia. Okay, so the idea is that you're going to do something which is shorter, more polished, and you're going to end up on Wikipedia. If you actually go on Wikipedia and look for statistical learning theory, it's populated by our slides pretty much because this was pretty successful. In the meantime, I think we didn't do this for the past couple of years. So now there is more stuff. There's more Wikipedia to rewrite. So for those of you who want to rewrite Wikipedia, there's your chance over there. You're going to get a grade for it. And that's pretty much it. So in terms of dates, again, those are tentative dates, but they should be more or less official. We are having a discussion, and we're going to let you know in, I guess, 1, maximum 2 weeks, what is going to be your requirement for this project. The two possibilities we're discussing is either a report, basically 4 pages, NIP style, plus appendix, or what we did in the past is that we just had a poster session. So the only thing you gave out was a poster that you presented in a day. Okay, so again, In one case, you just prepare a report and you submit it, we review it, and we tell you what's the grade, and that's it. The other version, you don't submit any report, but we have a 1 day where there is basically presentation of your project through a poster, and so the instructors are going to go around. We are discussing the different pros and cons of these two solutions. If you want to voice out your opinion, please send us an email. We're going to try to keep that in mind. And
or we take a vote next class.
So you better come prepared. I think that's pretty much it. Any questions about logistics?
There is one more thing. We need the set of your emails in order to communicate with you. We'll open up a website where you can put your email. We don't have yet the information. Will be on the website, and latest on Monday we'll tell you what to do. Any question? Yeah.
Should we go to the instructors or the TA about the project?
Yeah, so basically what usually happens is that we try to actually make an effort to come up with your own project. Then you submit it, then we give you feedback, and then we start a bit of a process. This way, typically, majority of projects are fine, and you know what you want to do. In a minority of cases, you are particularly interested in to find it. So the first step is usually on you. You try to come up with something, then we go a round of back and forth.
Could you talk a little more about the prerequisites or background you expect for people in the class?
Yeah, so again, jump in anytime. I think pretty much what we're going to do this year is that we're going to assume that you have taken machine learning before, that you know basic probability. Probably if you know what's the law of large number, that wouldn't hurt. We need you to know linear algebra very well. And if you heard the word derivative or gradient, you should not shiver. We're now, compared to the past, in the past there was a bunch more optimization and convex analysis. We toned it down a bit. There was a bunch of functional analysis. We toned it down quite a bit, and everything is going to be pretty much self-contained. Similarly, I think for the probability, the more statistical part, basically anything which is more advanced is going to be covered within the course and exposed during the course. We're not going to do math camp as we did in the past because we think there's no need.
So is there no Hilbert space theory or measure theory involved?
Say again?
Is there no Hilbert space theory or measure theory involved?
Well, I mean, there's going to be, Hilbert spaces are essentially big vector spaces, and we're going to take that point of view. I might give out the definition, but we're not going to. Last year, it was like one of the feature of this course is that we actually used it quite a bit. This year, we're going to use it in a more mundane way. Measure theory, no, that's too hard. Nobody knows it. That's it. Do you have more questions? Yeah, sorry. Yeah, I think the other.
Are you open to the final project being combined with another class where the application or data that you just said were not graded on here would be that project?
Yeah, I think again we assume that you are going to do an honest amount of work for this course, and we just require to do a machine learning project. That's the rule of the game. Everything which start to be a bit more complicated, we have to discuss. But I don't think in principle we have any. We're going to prevent things in principle. Another question.
Is the project individual based or group based?
I think, sorry, I skipped this, but we actually put one line about this regarding P-sets, and I guess pretty much the same rule applies to projects. So I think for both P-sets and project, you can, discuss and collaborate with somebody. For P-sets, you have to come up with your solution. You cannot just write down the same thing like that, 2 pieces of papers. You have to spend time to do the things by yourself. In the projects, again, you have to show that it's not one project made by 2 people, but it's actually, the same amount of work as 2 projects. So again, I don't think in principle there is any reason not to, but it's on you to clarify in which sense these are 2 projects.
Thanks.
Yeah.
Can you talk more about the coding on the project list?
Yeah, so basically in this course, even when we talk about algorithm, we don't really go into detail. We got the best a level of a couple of lines pseudocode. So we definitely don't go into more system aspects, but you don't even go into the level of like they actually kind of hand tuning or kind of going with your hands in actually implementing the algorithm. So one possibility is to say, this algorithm is not covered in class or be only sketched in class. I would like to come up coding up and do a library, okay, and do a piece of something, and I really want to spend time doing that. That's one possibility, okay. In the past, we had a couple of suggestions on things that could be done either in more in deep learning or more like a simpler, like shallow, like architectures. That's another possibility. Anything else?
Okay.
Perhaps just the last thing is, so every year this happens. Okay, we know it's going to happen. We try to avoid it, and it happens. So there are a bunch of overflow. We try to be extremely nasty the first few classes, so that some of you don't want to come anymore.
This is called the capacity control.
Exactly. It's called regularization.
We meet it quite a lot in learning theory.
So unfortunately, at this there are no classes. We try to find other classes. There are classrooms that are a bit larger than this, but essentially it's either this or 600 people or something. So then we don't see each other. So the only thing we came up with is this idea of streaming classes. Okay, we still have to decide it most likely is gonna be a private channel on YouTube. We're gonna give out the link, but so you'll be able to see the class on YouTube as they happen, and there might be for some of the classes possibility to watch them again offline. Okay, but this last thing is not going to be granted. But the streaming, I think, is going to be our solution to the overcrowding. Okay.
Thank you. So let me come to the motivation part of the class, kind of grand vision of CBMM, that's the Center for Brains, Minds and Machines, of which I'm the director, and the class is one of the educational enterprises of CBMM. And the interest of CBMM, I will say later, of this new MIT wide quest is the problem of intelligence. You could argue, I've been arguing for a while, that intelligence is not only one of the great problems in science, problem such as the origin of the universe or the origin of life or the structure of space and time, but it's probably the greatest one of all these great problems. And the reason is that if you can make progress in it, some progress, that means you'll be able to improve your own intelligence, your own thinking, have machines that help you think better, and thereby solve all other problems more easily. So that's the highest priority one. And clearly there is a scientific component, like the other great problems, the origin of life. There is probably not much money to be made if you discover what the origin of life was, but it's scientifically very interesting. And here we have that component. It's really a great scientific challenge to understand what the mind is, what intelligence is. This is, after all, what thinkers, philosophers included, have been busy with for the last several thousand years across the globe. But in addition, if you can make progress, also it's going to be very important for technology. It's not an accident that probably the 7 largest companies in the world right now, counting Google, Amazon, Apple, and so on, have big efforts in exactly this, in artificial intelligence. So it's science and engineering, and the bet at the Center for Brains, Mind and Machine, which started 5 years ago with funding from NSF, $50 million for 10 years, was exactly this: to make progress in understanding how the brain produces intelligence, creates intelligence, and also in replicating intelligence in machines. So the first part is science, the second part, strictly speaking, is engineering, and I'll speak more about it later. It's not necessary to believe that in order to build intelligent machines, you have to understand the human brain. That's an open question, whether that's the best way or not. It's a good bet, I think, and I'll come to back this later, that it's a good way to do it. Okay? And it's good also in itself because of its scientific aspect. All right. In fact, why am I speaking of science and engineering? By the way, science, I use this, what is science? There was this guy, I don't know if you know him, it was Francis Crick. He started all the molecular biology discipline in '53 with his paper with Jim Watson on the structure of the double helix of DNA. And he basically insisted that science is natural science. His definition of science was it's physics, it's chemistry, it's biology. Engineering is not, mathematics is not. They study not natural things, but artifacts, human artifacts, including mathematics, okay? So this is does not say that science is worse or better than engineering. Just say this is what, when I say science, this means studying natural things like the human brain. And when I say engineering, then I mean mathematics and computers and all of that stuff. By the way, this is Francis Crick and that is David Marr. That's another. Sorry? The other guy, I don't know him. If we look at what I think are the two most emblematic recent success stories in AI, it's my personal view, and it's partly because the two people involved were postdocs of mine, so that's I'm biased. But I think that the two stories, DeepMind and Mobileye, are quite striking in the last 5 years. DeepMind is this company which is now part of Google. There are more than 800 people in London publishing a lot of interesting papers. They became very well known when their system called AlphaGo beat the kind of unofficial champion of Go, which is this super chess game very popular in Asia. 2 years ago in Seoul, I was there. It was pretty amazing, and they've done a lot of other interesting things. But so this is in the world of games, and well, now we have machines that can learn by themselves to play not only Go but also chess and other games better than humans. And Mobileye is a company that was started by Amnon Shashua in Jerusalem, Israel, to do vision-based autonomous or semi-autonomous driving, and was bought less than a year ago by Intel for a lot of money. So if you look at the algorithms that are at the basis of these two successes, they are deep learning and reinforcement learning. Reinforcement learning, which was especially used for the system AlphaGo of DeepMind, has its origin in neuroscience work, back to Pavlov and Donald Hebb, and studying how rats solve a maze, how they navigate a maze. And deep learning is the basic architecture, not stochastic gradient descent, but the basic architecture of layers of neurons or units with local connectivity, so each unit looking at the small neighborhood of units below. This comes from a suggestion of David Huber and Thorsten Wiesel down the Charles River at Harvard, recording from the monkey's visual cortex back in the 60s. Okay, so this architecture, which was modeled, for instance, in the model we had here, is basically the same that is state-of-the-art in deep networks, like ResNets. This is the architecture, it's not the way you train. But the main point here is these two example of recent successes, AlphaGo and Mobileye, are both based on algorithms that have their origin in neuroscience. And so when people ask me what will be the next breakthrough in AI, I usually answer, I don't know, but there is a good chance that one of the next breakthroughs will also come from neuroscience, just based on history. Okay, so, and in fact, Demes said that there is actually a nice paper, this is an interview, but there is a nice paper making the point that if we really want to build intelligence machines, not just deep learning and classifiers and machines that play games, but if we want to really replicate intelligence, we have to look at neuroscience. How does this fit into what's happening at MIT? Well, in the following sense, CBMM is this national center funded by NSF, the tune of 50 million over 10 years. There are about 12 such centers right now in the United States in various scientific disciplines. This is about essentially the combination of machine learning, cognitive science, and neuroscience. We are housed in this building. There is a faculty that is across different institutions, that is around 20 or so people. The main faculty are from MIT and Harvard, and it's a combination of neuroscientists, cognitive scientists, computer scientists, and machine learning people. So, and we have as corporate partners the usual suspects like Microsoft and IBM and the companies that were originally small partners. They have become part of Google and the bigger ones. Anyway, we have, this is pure advertisement, but I must say truth in advertisement. We have a very successful summer school. If you are interested, you can apply. 35 students every summer, 3 weeks at Cape Cod, which is a nice place to be. And to get people, essentially to try to clone a new generation of scientists that combine knowledge both in the neuroscience and cognitive science, but also in machine learning. This has been going very well, and so the success of CBMM was one of the motivations for Rafael Rai, for MIT, to announce this MIT Quest in last February, which is essentially an attempt to try to get substantial funding to expand the CBMM model and machine learning across the institute. So providing tools, software, and software support, so engineering support across the various departments at MIT, and at the same time, ideally setting up other center-like teams like CBMM working on other aspects of intelligence. CBMM is right now focused mainly on visual intelligence, but there are other parts of intelligence, the problem of intelligence, like development of it, like emotional intelligence, and so on, which deserve efforts at least as big as CBMM itself. So that's the context, and in the history of MIT is pretty encouraging from this point of view, because So these are the recent years, the center and now the quest. But of course there was older times back in the 50s in which artificial intelligence started in part at MIT. It was the term was coined by Marvin Minsky and McCarthy back in the 60s. And of course, disciplines that are important for what I said, like cognitive science, linguistics, control, and information theory were all represented here. So the MIT Quest right now consists of a bridge, which is an effort to provide engineering support and software across the institute. So this is more like a project Athena, and then research on science and engineering, and the part which is most unique to MIT, the part where I think we are better than Google or Facebook and Amazon and so on, is really the intersection of the science and the engineering. I mean, difficult to compete with Google in terms of purely engineering. Too many people and good people. As I said, DeepMind alone has 850 people right now. But it's difficult for Google or DeepMind to create a neuroscience department, for instance. It's difficult to justify to their shareholders their recordings from the brain of monkeys. They would like that. So that's one advantage for us. But this course is really about engineering. It's more about the mathematics of machine learning. What I told you is just to say that this is not all there is if you are interested in intelligence and in what's going on at MIT. So, so even if you are not interested in neuroscience at all, I think that the next few years will be a golden age for applications involving machine learning. They're just starting with things like Alexa and autonomous driving and so on, and there is much more of that. So short term, you don't need the neuroscience. Okay. Now, let me tell you a little bit of theory of learning and why it's interesting. This is actually a slide that I modified a little bit over the years, but probably first version is at least 10 years ago. The fact that machine learning, I think, is becoming the most is a lingua franca, in the sense is a formal language that cuts across so many different aspects of computer science, from cryptography to systems. It's, people there are starting to use machine learning, and I think that the mathematics underlying it should be the formal language that one will have to know in computer science. So that's one reason for why you should have at least exposure to theory of learning, even if you are not interested in working as a theoretician in learning, but just interested in computer science. There is, just to give you a feeling of how quickly these things have been moving. This was, oops, no, okay. Well, Mobileye had a video here, but it's old anyway. As a sub part of their system, they're detecting pedestrians, and they have a certain rate of error.
In addition to preventing collisions, the system must sense the road at great details, including lane markings, curbs, barriers, obstructions, recognize a large vocabulary of traffic.
Okay, now 20 years earlier, we had a system. This was a project with Daimler-Benz, so Mercedes. This is a car, a Mercedes driving in the streets of Ulm. Ulm is a little town in the southern of Germany where there are such labs of Daimler are. It's also where Einstein was born. And so there was a system we had developed here that I was trained with images of people and was detecting pedestrians looking from the car. And you can see from this short movie that there are some false detection. There is traffic light, for instance. So at the time, we had about 1 error or false alarm every 3 frames. We're very happy about it. At the time, it looked like great scientific success. Now, 1 error every 3 frames is 10 errors per second. So it's completely unusable, right? Okay. 20 years later, with Mobileye, you have 1 error every, I don't know, 30,000 kilometers of driving, something like this. And roughly speaking, it's like doubling your accuracy every year for 20 years. Okay? And that's why machine learning is becoming so important. Why applications like Alexa are now becoming useful and fun to use. Okay. Now, statistical learning theory will start from supervised learning, which is still the most useful framework in terms of how well it works and understanding the theory of it. And here is the idea that you have a set of inputs, think of them as vectors, for instance, a pixel in an image, and outputs, often they're just labels, but say a number or a vector, and you are trying to, from this set of examples, could be a small number, it could be millions, you are trying to find a theory, a model, a function that maps inputs into output, even for value of the inputs that are not in the training set. That's the goal of supervised learning, and there is a simple metaphor for it, which is, fitting a curve, but it's not just fitting the points you have, but it's also from this knowledge, this is the training set, for each point in X, you have the value Y, you have your training set, but then what you'd like to be able to have is a box that tells you for any given X, the likely value of Y. So prediction in that sense. And there are at least 2 forms of this that you are interested in. One is regression, which I just described. You know the values of X, and you are interested in the values of Y, and the values of Y can be a real number or a set of real number, or classification, which is most common in many recent applications. For instance, you want to say, is this image a person or not? Okay, so it's just a binary label. This will be binary classification. Essentially, it's the same as a regression, but the domain of your output is just a binary. And how can you study this problem and come up with conditions under which you can say, okay, I can predict or not? Obviously, from what I said, just from having a few points, being able to predict the underlying curve looks totally impossible unless you know something more. And there is a formulation. We're going to go into formulation of this type during the class in terms of probabilities, there is an unknown probability distribution. If you know it, everything is fine, but suppose you don't know it, you know that there is, and then you have a set of data that are sampled IID, drawn randomly from this distribution. It's a known distribution. That's the training set. That's all you have. And then you have to, based on this training set, pick up a theory. You know, you have a space of theories, of models, and you have to pick up one based on your data that will have the ability to predict new data. So a learning algorithm, a way to do this is a map from the training set to the space of theories, of models, of our functions, and you'd like the function you pick, the model or the theory to be predictive. Now, what does that mean? Well, you can define an expected error is the error you expect to make in the future. You cannot really compute that because this is based, the V is, say, some measure of error. Is your, for instance, is f of xi minus yi square loss, or some other measure of error. But you don't know the mu, the distribution of your data, the unknown distribution. So this is, if you know that, you know what is the average error you're going to do, the error to be expected in the future. This is the expected loss. You cannot compute it. What you can compute is the error on your data for your f that you have chosen based on, say, on a learning algorithm. You can compute the empirical error, the error on your n data points. And then you can prove that certain algorithms for picking your function have the so-called property of generalization, in which the error of the empirical error of your function that you have picked up is approaching the expected error. And this in practice means that the error that you measure on your data, if the data set is large enough, is a good proxy for the error that you expect in the future. Right? And you can have guarantees that certain algorithms will have this property. And you know, you can joke. I mean, it's more complicated than this, but if you are a hedge fund manager and you have this algorithm that works very well on the training set, and you would like to know, can I bet $1 billion tomorrow based on the prediction? You know, you'd like to have the assurance that the performance on the training set is a good proxy for what will happen, so that you have a good likelihood not to lose your $1 billion. So these are why these guarantees can be important. What is interesting, I just mentioned briefly, but is that the condition for an algorithm, a learning algorithm, to have these properties of generalizations have kind of interesting philosophical implications. For instance, it turns out that a way to ensure that a theory is, or a model or a function that picked by your learning algorithm is predictive is that the space from which you choose this function, this model, is relatively small. It's like a physicist that chooses a theory relative to another one because it's more elegant, it's simpler. It's basically the same thing. Or the other one is that the one of stability, they're equivalent conditions, that the theory should not change for every new data that come in. In a sense, it's kind intuitively say that it's predictive well enough so that it should not change too often, right? But the fascinating thing, I think, of this is that this principle seems quite reasonable, and physicists have used this idea of an Occam razor, of elegance in a theory for a long time. But learning theory puts that in a very nice mathematical framework, telling you which conditions, under which condition, and how you can formulate this kind of results. So that's the philosophy part, but you should look at some of the things we'll see during the class from this point of view, that there are guidelines that are quite important in general, respectively of the mathematical details. We'll speak quite a bit about regularization algorithms and reproducing kernel hyperspace, a little bit less. This is one of the workhorses in machine learning until deep learning. Is an approach in which you say, I want to find a function, so this is like a model that minimizes the empirical error, does best in terms of minimizing the empirical error, and at the same time it minimizes some measure of complexity of the function. So this is the Occam razor part. This is the norm in a reproducing kernel hyperspace. For instance, is typically related to a measure of smoothness of the function. So I prefer smooth function. I pay a penalty if they are less smooth. And so it's a trade-off between fitting the training data and being smooth enough. The interesting part is that when you solve this minimization problem, you come up quite irrespectively of the form of V with a solution of this type, that you have that the function you want is a linear combination of kernels. This is like, think of this as, for instance, a Gaussian centered in xi and with value x minus xi square divided by sigma, right? E2. So this would be, and the f of x is a sum of this, and you can find for a given training set, you can find the alpha I that minimize the error on the training set. So that's the learning. So these are kernel machines, and the point I want to make here is that they are equivalent to one hidden layer networks. You can rewrite this equation here in this way, simply saying each of these circle is k, this is k center in x1, k center in x2, xn, and this is alpha 1, alpha 2, alpha n, and when an x come in, for instance, in this case the vector is two-dimensional, this comes in, this unit computes this value k of x coming in, and minus, if it's a Gaussian, it would be minus x1, and that value would be the activity here weighted by alpha 1, and then summated all here. So this kind of classical algorithm corresponds to shallow networks, and we'll see the difference with respect to deep networks during the class. Okay. So these are just little crumbs from the theory to give you some feeling of the kind of things we speak about. And let me give you now some kind of applications. These are essentially, there is a universe of interesting applications they can do just based on building blocks, which are networks like the one I've shown, that can be trained in a supervised way and combined with each other in different ways. One of the first one in my group was face detection. And it's kind of interesting. It's probably one of the easiest, faces are one of the easiest objects to recognize. And this is true for machine learning. They were the first, you know, each one of your phone has a little bit of this. You can put a square on the face. And we were among the first, together with CMU, to do an algorithm of this type back in the early 90s. You know, this was work by a student of mine, Sung. So there it works fine. This is an example of a mistake, of course, but you can understand why the pattern. In respect, you know, the algorithm does not know about context. And up there you see an interesting case of generalization in which the algorithm trained on a picture of faces actually is able to detect as a face also a line drawing. It was a little bit surprising for us. Now, later on, so like 3 or 4 years later, we started to look at pedestrians, and this is the example I showed you before. There were many other applications that we did using essentially the same building block of a supervised learning algorithm. We had categorization in video, we had graphics, speech recognition, text classification, application to option pricing, you know, derivative securities, and so on. One of them was predicting type of leukemia from gene data, from activity in the genes. Now it's something that is done quite standard way. Another one was reading out from neural activity in the brain of the monkey what the monkey was looking at. And the idea seems crazy, you know, you recall from activity in infratemporal cortex back here, and you're able to say what the monkey is looking at. It's not so surprising, but I tell you how it's done. You first record with several electrodes activities in the brain when the monkey look at different images, and then you build an algorithm that is trained with this data. That's the training set, images and activities. And then you can, so activities being the input of your algorithm and the label of the object being the output. And then when the monkey is exposed again to images that can be different but not too different, you can say, okay, the activities that I record now is similar to these ones I've seen before. Right? It's a bit better than just nearest neighbors, but that's the basic idea. And so this works pretty well. Another one, which is a bit more crazy, is you can do things like this. You can train a network to tell you not only the class of the object, but it can tell you, if you train it with enough images, say the pose, you know, the orientation of this object. You have shown several orientations, the training set, and then it can interpolate new ones. But then you can say, okay, why don't I use the same box, but with input and output reversed during training? So in other words, now I train a network in which the input is the view, the degree, and I want as output the image. You know, this is kind of inverse graphics. Inverse vision is graphics. And this can be done, and it leads to things like
more news in a moment.
This system that was done by a student of mine, in which you train a system. So this involves more than one block. I'm just simplifying. But it's the same idea. You train one system showing images, movies of a lady speaking, and so the input is the voice, the output is the movie, and now you replace the voice with the voice of a different person. So the training is done on one person, the different person, and it has to synthesize a movie, a new movie that is following the new voice. And so the system will be of this type. It learns for 4 minutes, and then you input a new stream of phonemes, a voice, a few seconds, and it will output a synthetic movie. And so this
with one light on and one room, I know you're up when I get home. With one small step upon the stair, I know your look.
And of course, it does not matter which language you do this. I can switch to Chinese. And
with one light on
Marilyn Monroe
and one room,
singing a modern song.
I know you're up
The training
when I
was not
get
very
home.
good, so
With one small step.
this was Kate Couric was quite well known how many years ago? 15 or so, as an anchor in the Today Show.
Don't believe everything you see or hear. A graduate student at the Massachusetts Institute of Technology has developed a computer program that can manipulate video to make it appear as if you've spoken or sung words that in reality you have not, even in a language you can't speak. Tony Izzat is the MIT student who developed the program speech animation. From New York, not from the beaches of Cannes, TV news legend Walter Cronkite. He'll be hosting this year's 61st annual George Foster Peabody Awards ceremony on Monday. We'll talk with him about that.
And this is now the voice of another anchor.
The new technology can take anyone's voice,
Elisa
including mine, and by reprocessing it through a computer, my voice can sound and look as if it's coming out of someone else's mouth.
The real
NBC News, Cambridge, Massachusetts, and New York.
And the real one is here.
The meeting was frank. The meeting was frank.
One sentence, one video.
53%. 53%. More news in a moment. More news in a moment. It's a matter of money. It's a matter of money. That's all for tonight. That's all for tonight. It could take months. It could take months.
So, when we had the naive subjects looking at them, they were not able to really say which ones was real and which ones was synthetic. I guess they're called fake news these days. You can do other things using this kind of techniques. Also, this is all the work. It's Thomas Federer was postdoc of mine, you can take a single image of Tom Hanks and create a 3D model out of it. And the way you do that is that you have 3D scans of about 200 faces, and then you can, from the single image, fit a linear combination of the 200 scans to this single image. This is really based on the fact that human faces are a relatively low-dimensional space, turns out. And so once you have a 3D model of Tom Hanks, you can do a lot of things, like change his expression, change the direction of the illumination, and so on. And you do the same here with Audrey Hepburn, and these kind of things are quite similar to an approach that has been taking quite a lot of prominence in the recent couple of years in machine learning, is GANs, is generative adversarial networks. We'll have a class about it in October, in which you can, for instance, map, say, inputs that don't have color to get color for them, so colorization, or to match, to provide a system that can, from edges of an object, give you a picture of an object. It's kind of similar approach, similar results, different techniques, similar results in the sense that it's doing something like this. And I, just for historical pleasure, I just managed to dig out something we did long ago, which was based on this. You can imagine I could have a system trained in a supervised way to estimate pose, and then and other parameters, and then another system that synthesizes images based on this pose. And in this way, have a very low bandwidth teleconferencing system. And so this is what we did. Sometime. I heard the music.
After
Oh, yeah.
For this teleconferencing project, we have developed an example-based technique for image compression based on learning networks, like the one shown in this diagram. The system consists of an analysis network, which estimates pose and expression parameters from images, and of a synthesis network, which computes new images from the parameter values associated with each one of those images. After training, the analysis network estimates for each new frame on the left the 3 parameter values which are sent to the synthesis network that synthesizes the corresponding frame on the right. A brief composite sequence, again of 180 frames, is shown here. On the left of the screen, you see the real image sequence, and on the right side of the screen, you can see the synthetic one. In this case, each real frame on the left is compressed to 3 parameter values, which are used to reconstruct the frames at the receiver's site.
Okay. So this is mainly for fun, to show you some old applications. The main point is that there are a lot of things that you can do if you use, say, a supervised module that can learn from examples. and combining them in different ways. I'm not saying this is the only thing that you can get from machine learning, but even that by itself can be used in a lot of interesting application by building on it different types of architectures. And the last thing I want to mention in the last 5 or so minutes is a few things we'll see about deep learning. We'll try to look at deep learning, and I think you all know what is it. It's a layered system in terms of the architecture. Input there, the output is here. Typically, in this example, the input is an image. Here is a label of what is the image. You can think of that as a composition of functions, each layer being one of the components. It can do pretty interesting things that came to the forefront of computer vision when we did very well in labeling this data set called ImageNet. Here are some examples. A few years ago, it's 1,000 classes, 1 million images, relatively large images, 300 by 300 pixels. The architecture, as you probably know, is quite simple in terms of what's going on. You have, in each one of those layers, you have a set of units, neurons. Each unit is submitting the incoming inputs from the previous layers or the input. Each of these lines has a weight. What the unit does after the summation is to pass that number, the sum, through a nonlinearity, which is an RLU, a rectified linear unit. And this is then the output of the neuron. The weights are what you try to learn during training. You try to learn during training by changing the weights in such a way that they minimize the error over the training set. And the error could be a square loss or something like, for instance, a cross entropy error or the logistic error in the case of binary classification. We'll see all of these kind of things. You're using, to do that, modification of gradient descent. In which you are following the gradient, changing the weights according to the gradient over the loss function, or changes modification of it, like stochastic gradient descent. And okay, that's the essence of it. And the kind of question we'll look at are about approximation, optimization, and machine learning theory. One is, the first one can be phrased by saying, why and when are deep networks, multiple layers, better than shallow networks? And that's the first question. And the second one is about optimization. It turns out that it's relatively easy in many cases to find good minima during optimization, good set of the weights. Why is that so relatively simple? These problems are very large optimization problems. They are non-convex. They have millions of data points, like 1 million images in ImageNet. The network that you're using have millions of parameters. So the face of it seems quite strange that you can relatively easily optimize. And the other question is why can this network do pretty well on new data, generalize well, despite the fact that the typical use is in the over-parameterized domain, in the sense that you typically have more weights in the networks than you have data points. Okay? So we'll address all of this at some point in the class towards the end, and I'm not going through the answer yet, but let me summarize here these 3 questions that will hopefully build upon our answer will build upon what we have seen during the whole class. In fact, one of the conclusions seems to be that classical learning theory, the one developed mostly for shallow networks, also applies to deep networks. This would be one of the messages of the class. And part of what would be interesting for you to think about is also, I think there are going to be other breakthroughs in machine learning, many of them. And these are kind of some possibility in terms of combining, basic supervised learning blocks, for instance, like is done in GANs, to come up with essentially new architectures good for new applications. There is the whole question of how to deal with the fact that deep networks requires millions of examples, and we humans or human children do not require millions of examples. Right? So there is possibility that you may have ways to train a network that involve time, essentially training to predict what happens next, or predict the next frame. In that case, you don't need a label, because it will come next. But there are similar situations in which, for instance, suppose that I say I want to predict the color of this object in the image, and I give you a black and white images. So the training set is black and white images, that the output will be the colored images. We'll see that in a talk by Philip Isola. But if you think about it, this is something that biology could do without need of somebody labeling the images. Our visual system could take just a black and white version. It has also the color. And so the network could be trained on the black-white to predict the color. They are both available. We don't need a team of people labeling the images. And the same for the next frame. And there may be also new interesting, I hope Shimon Ullman will speak about some interesting work or a slightly different architecture from deep networks for specific high-level learning of concepts. So the possibility of modifying the basic feed-forward architecture. And also, again, this connected to biology, learning algorithms that are different from stochastic gradient descent, which seems biologically very implausible. It seems implausible. I'm not saying impossible, but implausible that neurons can compute derivatives the way you need for gradient descent. And so one can think of different algorithms based more on coincidence of activity between inputs from the bottom and signal from the top. Anyway, these are really kind of musing and dreams and conjectures, but just to mention that I think maybe some of them, like certainly other ones, are possible breakthroughs in the near future. So let me finish here you know, you can see machine learning as a paradigm for computer science. The old computer science is programming. The new one with machine learning today, instead of hiring expensive programmers, you hire cheap labelers that labels data. And next you may have to open schools for your other, like children. Okay. See you next Monday.